A lot of questions in physics about escape velocity. And escape velocity is how much kinetic energy really is needed at the current location to get the object to move infinitely far away. Okay, there's no like one threshold. There's no one area where gravity stops working. We're pulled by everything across the universe. But basically, you are outside the influence of the Earth if you could make it infinitely far away with your current energy. Okay? If you don't have enough kinetic energy, you could think of it as throwing an object up and it getting pulled back down. But if we can get it infinitely far away, then the gravitation is zero. Okay? So to find that escape velocity, think of it as throwing a ball up. How high does it go? Well, how high? We want to find a height of infinity is really what we're doing there. So let me show you. I drew it sideways, but here's what we've got. We've got a total energy here that's made of potential and kinetic. And remember, potential, we're going to have to use that more complicated gravitational potential energy equation. And then up, I'm just going to make a break there. This is infinitely far away, and remember, potential energy is defined as zero infinitely far away. And the kinetic energy, think of how high, when we say how high a ball goes. Up at the top, we consider the velocity to be zero. So the same thing is going to happen here. We want to get it up to a point where the total energy is zero. It doesn't have to be moving, and it has a potential energy of zero because it is infinitely far away. So that's kind of a big deal right there. That total energy is going to have to be zero. Well, guess what? That means if energy is conserved, the total energy here has to be zero. Oh, zero. So something sitting still would work. No, because potential energy is this huge negative number near the Earth's surface, for example. But we can do this, by the way, from an orbit. It's an orbit or something, and how much energy would we have to add? But I'm just going to do it from the Earth's surface. So this is going to be this negative g m1 m2 over r. And we're going to try to find that kinetic energy so we can figure out what the velocity is. Okay, I'm going to do that for the Earth and a ball. I'm just going to say it's going to be a 1 kilogram ball. 1 kilogram ball. Okay, and so once again, we're just doing a standard conservation of energy type of problem. E total equals E total prime. U plus K equals U prime plus K prime. Infinitely far away, R equals infinity means this is zero. V is zero up at the top, means that's zero. So 0 equals U plus K. Once we find out what that potential energy is, K is going to be the positive of that. That's how much we have to add. So the negative G m1 m2 over R squared, over R plus the kinetic energy, 1/2 mv squared, mass of the object that we throw. Okay, so let's do it here for the Earth. Let's give ourselves a little more room. 0 equals negative 6.67 e minus 11 times the mass of the Earth. I'm going to use 5.98 e24 times the mass of the object, 1 kilogram, divided by, no, I didn't even leave myself nearly enough room, by the way. That's a big equation. Divided by the radius of the Earth. I'm going to use 6.37 e 6.37 times 10 to the 6th meters, plus 1/2 m, I don't know why I did that, m v squared equals 0. Notice, by the way, this mass of the object, is going to cancel out, right? Yeah, I had it as 1, but we could cancel out the mass of the object, divide both sides by mass of the object. So this velocity doesn't depend on the mass of the object. It only depends on the planet and how far away you start from the planet. We're going to start out at the Earth's surface. I'm going to punch in some numbers. I really probably should have done this before, but 6.667 times 10 to the negative 11 times 5 point, that's supposed to be 0.98 times 10 to the 24 divided by 6.37 times 10 to the 6th ends up being negative 6.26, etc., times 10 to the 7th joules. So once again, the kinetic energy has to cancel out this. The kinetic energy will be positive 6.26 times 10 to the 7th to get it up to infinitely far away. So this ends up being 1/2 v squared equals 0. And so when we take that and we solve for v, what we get is 11,190 is what we call the escape velocity, meters per second. Oop, almost put squared, meters per second. That's the escape velocity. Okay. Now, we can actually write a nice equation for the escape velocity in more general terms. If I just take this equation there, okay, and I say negative g m1 m2 over r plus 1/2 mass of the object, I'll call it m2 v squared equals 0. The mass of the object, again, I can cancel out. And the velocity will end up being equal to the square root of 2gm1 over r. And this is the planet. And this is the distance from the planet where you start. Okay, so that will always give you that escape velocity. Let's look at a couple of things. When you look at things like the moon with a very, very small mass, this escape velocity is so small that actually the kinetic energy of atmospheric particles, if there's ever any particles in the atmosphere, they have enough kinetic energy to leave. That's why the moon does not have a significant atmosphere. There needs to be a very big mass in relation to the radius for planets to have a decent atmosphere. Jupiter and Saturn are so massive that they're almost all atmosphere. They're gas planets. You could think of them as almost all atmosphere. So at any rate, that's the escape velocity. That's how we use conservation of energy to figure out the escape velocity for planets.